let's talk about what we were discussing last time. What we ended off talking about the Pauli Exclusion Principle. Pauli Exclusion Principle. And we said we have two definitions or two formulations of it that we discussed last time. Can anyone tell me one of those formulations?
So no more than 2 electrons can occupy an orbital with the same spin, or you can't have 2 electrons on the same orbital with the same spin.
Right, can't have 2 electrons on the same orbital with the same spin. They have to have different sets of quantum numbers. The other one had to deal with wave functions. So if I have like electron 1 and electron 2, and I switch those labels, what has to be true?
The negative sign in front of the wave function.
Yep, that must be true, right?
Right.
Okay. And last time we got to this point and we wanted to start describing why is this way? Why is this true? Okay. So and we said we have a wave function like this. If we wanted to make this wave function simpler or less complicated, if we actually want to solve this system, what approximation do we need to make?
The BL one.
I'm sorry, what'd you say? I couldn't hear you.
The BL one.
The Born-Oppenheimer approximation?
Yeah, no, that's wrong.
I mean, we will make that eventually, but not right now. What other one have we dealt with recently?
The orbital approximation?
Yep. And what does the orbital approximation say? Like, how are we going to express this wave function?
Would it be is equal to the 0 with the line through it times r?
Yeah. So we've changed r out just for these
Oh,
numbers.
so it'd be 1.
Yeah. And 2, like that. Okay, but we're going to be looking at helium. So for helium, one, two, we're going to have almost the same thing, but we're going to specify that these orbitals, we're going to say 1s and 1s. So those are subscripts underneath them. But we're forgetting one important parameter, one that we discussed a little bit. We're leaving off the electronic spin. So however, we need to include spin. So like that m sub s, positive 1/2, negative 1/2. Now for the spin part of the wave function, we're going to indicate an up spin and a down spin with an alpha and a beta. So the spin part of the wave function will be denoted as either alpha or beta spin, depending on the values of m sub s. So like this one, we'll say the m sub s. What are the only two possible values of m sub s?
1/2, negative 1/2.
Yeah. We'll call this one positive 1/2, this one negative 1/2. Some people might have different definitions, but that's what's meant by alpha and beta. Okay, So now let's write out all the possible wave functions we could have. So the several possible wave functions. For helium. The first one we could have 1s, electron number 1, electron number 1 alpha, 1s2, alpha 2. And right now we're going to assume we don't know anything about the Pauli exclusion principle, okay? We can tell this one's wrong already though. Can anyone give me a reason for why?
They have the same spin.
Yeah, they have the same spin. Pauli exclusion principle says that can't happen. But
I thought we were ignoring it.
we are. But keep that in mind. We're ignoring it for now. Okay. Give me another possibility for the wave function.
Changing alpha to a beta.
Sure. Okay. Give me another one.
1 alpha, 1 beta.
Okay. Give me another possibility.
Beta then alpha.
Okay, so those are the possible combinations. Now, there are two different types of orbitals we're talking about here. People sometimes call like this beta and alpha part, that's sometimes called the spin orbital. And sometimes these orbitals here, these are often called spatial orbitals. The hardest part with this is there's terminology. Some people consider this whole part up top, like that part right there, or this whole thing to be a spin orbital. In our case, we're going to just call these alpha and beta spin orbitals. Okay, everybody got that scrambled down? Okay. So, but the problem is only there's some experimental evidence that rules out 2 of these. So, however, only 2 of these functions are experimentally observed. Because if you look at the spin angular momentum of helium, can anyone guess what the value is going to be? Remember,
0.
spin. What was that, Josh?
0. Will they
That's
cancel
0.
out?
Yep, they cancel out because the upspin and the downspin are meant to cancel one another out. So therefore, when we look back at this set, which ones are we going to ignore?
The ones are the same.
Yeah, when you say the same what?
The same spin.
Yep. So these first two, they're garbage. Get them out of here. I don't know. I've been watching a lot of Governor Cuomo, and I'm like, yeah, New Yorker accent. I'm good. I've never really liked the guy too much, but he's pretty funny.
He threatened to sue Rhode Island.
Uh-oh.
Look out.
It's a sore subject for Maddie.
Yeah.
This is funny because that would like cost my parents just so much money.
So these two are the ones that we want, are the only possible wave functions. Okay, so then we have two possibilities. So let's ask the question, which one is acceptable? The question, then which is the right one? Which is an acceptable wave function? And now these particles are meant to be indistinguishable. Like we do give them labels like electron number 1 and electron number 2, but we can't ever really know which one's electron number 1 and which one's electron number 2. So we can't actually only have one of these. So if we select one, one wave function, then we know the exact wave function. Of each electron. Oops, each electron. And we can't do that. The electrons have to be indistinguishable from one another. So therefore, this is impossible. Okay, so then we'll ask another question. How do we deal with this then?
Just say it has like a super state.
Yep, there is superposition. So just like with Schrodinger's cat, where it seemed like it was impossible to know if the cat was dead or alive, we said it was a superposition of both of these states. So it is a superposition. And we use a linear combination to describe superpositions. So like with our cat, yeah, the wave function of the cat was 1 over a square root of 2 for that normalization constant. Rho alive, excuse me, not rho, phi dead. We also had our quantum chicken, wasn't it like something like?
We did have the quantum chicken, you're right.
Yeah, we had the quantum chicken. What? There was like.
You had the rooster and then your attempt of a chicken. So I think that.
Oh, okay.
Or maybe that was me.
Draw it again.
Well, let's see. Oh man, that looks like a duck. There we go. Need more feathers. We got one like there was that one, and then there was like a I don't know. There was a real sad looking one.
Yeah, the McDonald's chicken, I think is what.
Yeah, yeah, the one that's going right to pink slime.
Yeah.
That one looks like there's something wrong with it.
Yeah,
Your doctor
yeah, that's why
says
he's going to
That's-
McDonald's.
That's what McDonald's farms do to chickens. Yeah.
Should put that baby on my senior sum.
The quantum chicken, man. Okay, then, so looking at that, looking at these, we can make a linear combination of the two functions that we have. So then we can construct wave functions for helium from a linear combination. Okay, so we got two possibilities. We got a symmetric case, and we're going to denote that symmetric, psi-symmetric, electron 1 and 2, 1s1, alpha 1, 1s2, beta 2, plus s1, beta 1, phi 1s2, alpha 2. Now this function is not normalized. If we wanted to normalize it, what do we need out front?
And
squared.
or 1 over red.
Yeah, 1 over 2, yep, like that. So there's the symmetric case. Can you guess what the other possibility is going to be?
Symmetric.
What was that?
If not symmetric.
Yep, asymmetric.
Good job, Captain Doctor.
And how are these two functions going to differ?
Alpha and beta are going to switch.
Not quite.
Oh wait, oh no. Is it going to be negative?
Yep, there's a negative. There's just a minus sign here instead of positive. Beta 2 minus 1s1. Okay. So then we arrive at the question, which one of these is right? Is the symmetric or is the asymmetric wave function correct? Question. Which wave function is the right one then? Okay. So now if we look back at our definition of the Pauli Exclusion Principle, we said the wave function must satisfy the following. If we switch those labels, we get a negative sign. So what this tells us, can anyone guess which one of these two is going to be the right one?
Asymmetric.
Yep. Okay, so let's test these. So testing psi-symmetric.
Is that what asymmetric stands for? Anti?
Yeah, asymmetric, anti-symmetric. Yep.
Never realized that before.
I think it's just a shortened way of saying anti-symmetric. Oh wait, asymmetry says no symmetry, right?
Yeah, probably.
It makes sense if it's anti. I just never thought
No, I
I-
think it's
I don't
different.
know.
I think asymmetric is different from anti-symmetric.
I think it
Yeah.
is too now.
Hey Google, is there a difference between asymmetric and anti-symmetric?
Let's see.
What did you say, Maddie?
What's Google got to say?
There's a slight difference between the two.
I believe like the whole asymmetric and abiotic, I think it's
Yes.
Latin. It means no.
I'm sorry, Ellie, could you say that one more time?
Asymmetric, like abiotic, it's Latin and it means no.
No. Okay, so it says no symmetry.
Yeah.
So is
okay,
that really different
Will
from
said
anti?
there's like a
then?
difference. It's about the linear or something.
it is in terms of mathematics. So there's something called being reflexive. So what is it? Anti-symmetric can be reflexive. Asymmetric cannot be reflexive. So if we're being real nitpicky mathematics wise, yes, there is a difference. For our purposes, we're going to ignore it, but we're going to say anti-symmetric from now on to be technically correct, the best kind of correct.
Do we ever use quaternions in this class?
No, I've never even heard of that term.
Oh, okay. Like it's
Okay,
like
John, let's calm down.
Yeah.
We're already at peak hour.
it's like
Solution's not a big deal.
I'm such a jerk.
What are those?
so it's so like we have like the real number system, then we have the complex number system. The quaternions are based off of both and give you like a 4-term system. I guess it's really good for describing 3D rotations and are used generally in quantum mechanics and things.
No,
Where did
no, we
you
are
learn
not.
that?
Yeah, come on, man.
It's
Where
like
did you-
it's like I, J, and K is what it uses.
Oh,
Oh.
okay. I think
Yeah.
it can be done. I think there are some codes that actually do utilize it.
Yeah, a lot of like gaming and like video stuff uses it. I guess because it's just more efficient.
Dr. Simpson, I think you repeated the same way. Oh, wait, no, you did 2 then 1 that time? Oh, you just swapped
Yep.
them out.
We're writing what we had previously. Now we're switching them around. So we got 2 alpha 2,
Interesting.
1, beta 1 plus 1 alpha 1 2 beta 2. Okay. Looking at these two functions, are they different?
Yes. No. Yes.
Um,
Final answer, yes.
Take
No,
the average of them.
yeah, because it's commutative.
No, they work out to be the same.
Yep, they are the same. So these two are the same. Therefore, psi symmetric of 1, 2 is equal to psi symmetric to 1. Therefore, it is not anti-symmetric and doesn't follow the Pauli Exclusion Principle. What about the other way around? So testing psi asym. We'll have psi asym 1, 2. Same thing as last time, except with a minus sign in the middle. Two plus 2, 1. and a lot of writing.
Should this be negative asim, or are we just saying that?
Right now we're just looking at the two functions, asim 1, 2, and then asim 2, 1.
All right.
Okay?
Yeah.
So now, are these functions different?
Yes,
Mm-hmm.
because they don't commute.
If we ignore the negative sign right now, this term is the same as which term?
Second term.
Yep.
Yeah, second, the second term up there.
And now this in the purple, this is the same as that term, right? But that negative sign makes them different. If we wanted these two to be the same function, what could you do mathematically to make them the same function?
Put a negative up front.
Yeah, if you hit a negative out front, then
But wouldn't the first
would be
term
true.
still be? Oh, okay. I see what you're saying. Okay.
Yep, so if you pull the -1 out of here,
Mm-hmm.
or you multiplied this system by -1, these two would switch spots. So this is anti-symmetric. So we found our wave function. This is our wave function right here. Woo! So we have our wave function. Which is pretty cool. So if we're talking about the helium atom, that's equal to our asymmetric function. Now everyone can see writing this out numerous times sucked. It ate up a lot of time. And we could actually describe it pretty easily with something we've done in the past. So this is why we talked about determinants. We're going to express these wave functions as determinants from here on out. So that way we don't have to keep writing this junk over and over and over again. So this can be better represented as a Slater determinant. Slater was pretty important in terms of mathematics and quantum mechanics. You might have heard of Slater orbitals or Slater functions. So let's try to represent helium. So we wanted a determinant. Anybody have an idea of the size of the determinant we're going to use for 2 electrons?
2 by 2.
Yep, a 2 by 2.
Here?
1s1, alpha 1, s1, beta 1, 1s2, alpha 2.
Did we do this already in inorganic?
We did do something pretty similar. It wasn't the exact same, but we were looking at determinant. We were looking at matrices. Like you're thinking of the irreducible representations and that stuff.
Yeah.
Yep. Okay, and that's equal to the asymmetric case. Now, some people define these differently. Like you could flip these if you wanted to. So you could do like all the 2 stuff along here and so on. They should work out to be approximate. So the general form of this determinant is the following. So let's say we have a multi-electron system, 1, 2, and it goes to n number of electrons. We have 1 over square root of n, and a big determinant. That's 1, alpha 1. What term's going to come down here?
I'm confused. You're solving the determinant right now?
We're building a determinant for a multi-electron system.
Would it be the bottom right corner one?
Yeah, so you're saying this guy?
I said right, but yeah, that
Oh.
one. makes sense.
Sorry, left and right are tough for me.
No, it's okay. I was right then, if I was wrong.
And so this is going to continue down till we get to our, I don't know, our n number of electron. What's going to come next on this side?
Is it going to stay as a 1s even as you increase in the number of electrons?
Not all the time. How many electrons can the 1s hold in total?
2.
2.
So
So
that's-
after we get through the second column, we're going to have to change. So what's this one going to look like?
2.
Actually, we're going to stick with 1. What comes next?
2.
Nope, not 2.
Beta.
Yeah,
Beta.
Oh, 2 does come next here.
Yeah.
All right, and just as Josh said, what about after, like, is it always 1s? No, because it's going to change to whatever orbital we need to accommodate for. So to indicate that, we're just going to put phi sub m, indicating some other higher orbital. It could be like a 3d, a 4f, anything, but it's going to go in order. We'll do another example of another atom so you can see. 1, we'll do beta 1, M2, beta 2. There's a bird going nuts outside my window.
Jim
You
was
guys,
probably got it.
you guys can't hear it, right?
No.
Okay.
We're
Okay.
writing so.
We're writing a lot today. Okay, so let's do an example. Let's construct a Slater determinant for a lithium atom. Am I okay to move this up?
Yeah.
For example, construct a Slater determinant for lithium. Okay, how many electrons does lithium have again?
3.
Yep. So we're going to have 3 coordinates, 1, 2, 3. Tell me what comes next.
I 1s 1 alpha 1.
Yep, so 1s, 1, alpha 1.
And then beta as well in there.
Okay, yep, so you want beta here. Can anyone tell me any other terms?
Be the same thing
It will
underneath.
be phi 1s 2 beta 2
Where's
or
that one
alpha
gonna
2.
go?
It'll be alpha.
And then we had, yeah, the other one that you said. What were you saying, Tara?
Nothing.
Nothing? It sounded like you were gonna say something. We're missing a normalization factor out here. What do we need?
Square root of it.
1 over radical 3.
Square root of 3. What else do we need? Or what
Then
size matrix
phi-
are we going to
We can do
have?
the same thing for 3.
Alpha 3, 1s, 3, beta 3. But what size matrix do we need for a 3-electron system?
3 by 3.
3 by 3. So we're missing that last column.
That's unfortunate.
Would it be a gamma?
Nope, no gamma.
Can we do shark fin?
Nope, no shark fin.
It's gonna be 0 with the line through it, and then
So
M is.
let's write out the electron configuration for lithium. We already know what it is. What is it?
1s2, 2s1.
Oh, it's going to be just 2s and then alpha again, isn't it?
Mm-hmm.
All right.
2s,
That's
1.
lame.
Changing.
I was hoping for a new symbol.
He's trying to trick us.
No, spice it up.
Spice it up.
Word is out of fashion.
Now, for this last column, you could choose either alpha or beta. It really doesn't matter. We just selected alpha because we started with this one being spin up. Okay. Does everyone feel comfortable with that?
Yeah.
Everybody feel like they could do that on a quiz?
Yep.
I thought you said it was gonna be shorter though than the other way of writing it, and I feel like this is still just as long.
Well, this is a 3 by 3, right?
You're going to have us do 4x4s, aren't you?
So we
Maybe
would have
5
to
by 5s.
do, you would have to do the determinant of that. So you would have like a bunch of
Oh, I
these
see what you're saying,
terms.
because so that's just a 1x1 technically up there.
This is a 2 by 2 matrix. So this is that guy, which you can see it gets way more complex as we keep adding.
It's not gonna fit on a piece of paper unless you put it in the matrix.
Okay. So that's really all I wanted to discuss this class.